AI Math Olympiad winner is currently open source, built on top of open source model, and it uses a lot of interesting techniques that ultimately gave the team $131,000 first place. We're going to discuss the model that they use, the techniques that they use, but before all of that, I would like to quickly show you a demo. I went ahead and asked what's the difference, the weight difference between 1 kilo feathers and 1 kilo of iron bar. And as you can see here with the solution, first it generates some kind of reasoning, and based on the reasoning it writes Python code, then it executes that Python code, and then based on that it summarizes the answer and gives you the final answer, which in this case is a correct answer. So this solution is a decent solution. What is this IMO? IMO, I don't know how do you call it. I'm just calling it IMO. Artificial Intelligence Mathematical Olympiad. So this is a overall $10 million AI Mathematical Olympiad prize, and there are some interesting people who are evaluating this, including Terence Tao. If you do not know Terence Tao, immediately you should pause this video, go Google Terence Tao. So this is a huge prize, and the intention is, I think, to see if AI models can solve intermediate high school level math, and the benchmark here is that the Gemma 7 billion parameter model solved 3 problems out of 50, so whoever is doing much better than that will be the winner, of course. And they had multiple prizes. One of the prizes is the early share prize, which is a $10,000 prize. Almost all the prize winners have quoted that one particular solution that they used from Abdul Rafi, who has got a public notebook. I'm not covering that in this video, but if there is an interest, I will do that separately. But for this prize, we are going to talk about the first place solution, that is the solution called Numina Math 7 billion parameter model, TIR. TIR in this particular case stands for Tool Integrated Reasoning. What is a tool integrated reasoning? A tool integrated reasoning is where you just do not generate a solution directly from a model. Rather, you would use a tool to generate a solution. So there is a reasoning that is integrated with tool. So if you see in the first step, the way they went about this is, in the first step, they took natural language reasoning data and they fine-tuned the model. They took the existing pre-trained model and they fine-tuned the model. This is probably a slap on my face for creating a video recently to say that stop fine-tuning. This is a perfect use case where fine-tuning has made a difference, and fine-tuning is of course required. So yeah, that's a slap on my face. And this first stage is where natural language reasoning and fine-tuning using natural language data. We'll further deep dive into it. The second stage is where they create a code nested tool integration data, and finally they generate the reasoning and the tool, the code, and the code gets executed on the tool and you get the final answer. And this is something that they credit to Microsoft's Tora paper. So that is a paper that they said that they followed the approach, a tool integrated reasoning agent for mathematical problem solving. Now, to start with, this solution is built by a bunch of people, and one of them is an employee at Hugging Face, I guess. And they've got a 2-stage approach, and the 2 stages, the first base model that they took is DeepSeek Math base 7 billion parameter model. Yes, it is the same model from China, which is the DeepSeek family of models. So they used the DeepSeek Math base 7 billion parameter model. They took that model and fine-tuned a model to act as a reasoning agent. So this is the reasoning agent that they used, and they used a decoding algorithm for TIR, tool integrated reasoning, that helps with code execution feedback. And they also had like multiple other techniques, because this competition had a bunch of weird rules that you would not probably see. If you're familiar with Kaggle, probably you might know this. Otherwise, let me quickly show you what are the rules. One, we already know that the baseline is a 3 out of 50, which is the Gemma 7 billion parameter model. So anytime you cross 3 above 3, you have already done something better. But also the early share pricing that I said, that is a high scoring public notebook, which means somebody openly sharing a solution where they must have got at least 20 out of 50. So most of these winners already got a head start thanks to this one solution that gave them 20 out of 50. So all they were doing is improvement on top of it. I'm not saying that that is a smaller task, like, because as you increase in accuracy, it is always difficult to hit the higher one. It's like, you're in the sprint and Olympics. Every millisecond matters. So what is the condition that they've given? So you can run this solution only with less than 9 hours runtime on CPU, less than 9 hours runtime on GPU. You will not be given any internet access, and you are free to use any free publicly available or free data, and including pre-trained models. So this is the most important part, because if you get like 24 hours of GPU, that could be a totally different case. But all these prize winners had to fit their solution in which it can run within 9 hours of GPU runtime. So that is one of the reason you would see most of the solutions uses VLLM. So VLLM we have covered previously on the channel, and a lot of these solutions, I went ahead and then read all the solutions the solutions they have shared publicly, and most of them used VLLM because of the speed. So that is something that we are clear with. So the base model is DeepSeek Math base 7 billion parameter model, and in this particular winner has used multiple open source libraries: TRL, PyTorch, VLLM, DeepSpeed. And the model that they trained, they used 8 H100 GPUs, and it took 10 hours to train. That's quite a beefy GPU and a lot of time to train. The final model is what they have shared here in Hugging Faces Model Hub, which you can go ahead and then use it. And as you can see here, this is a text generation model, and this model technically generates a code that will be executed. So as you can see here, it generates a code that you can execute. Right now it doesn't execute in a notebook, but that is technically what they have generated. How did they go about building this? The training recipe is as follows. So they took a model, and they took a fine-tuning recipe from a paper called Mu Math Code paper. So they took the recipe here, Mu Math Code, combining tool usage, large language models with multi-perspective data augmentation for mathematical reasoning. I'm not diving into the paper, but to quickly say that for every mathematical problem, they created 2 stages. In the first stage, they took the mathematical problem and then they converted that mathematical problem into a diverse set of natural language math problems and solutions, where each solution is templated with chain of thought reasoning. So you take, for example, if you have a solution question like this: what is the difference between 1 kilo of feathers and 1 kilo of iron bar? Now this question is split into a large natural language reasoning. You'll be like, okay, if I have to do this, I have to find the difference between these. Okay, for me to find the difference between this, I have to understand the material here, I have to understand the material here, I have to find the number here, I have to find the number. So you pretty much create the entire reasoning. But in this case, I don't think they generated a synthetic dataset. They used existing dataset and created that fine tuning. The first stage, they used an existing dataset based on this particular paper, Mu Math, and then they fine tuned the first stage. In the second stage, they used the synthetic dataset of tool integrated reasoning, where each math problem is decomposed into a sequence of rationals, Python programs, and their outputs. So you see 3 things. One is the reasoning or the rational, the Python program, and their output. So in the first stage, you only fine tune the model with the solution reasoning, but you make sure that it is like the chain of thought template, so that the model understands, model has a reasoning to answer. But in the second stage, you are not going to rely on model's answering capability. Rather, you are converting that into a rational, a Python program, and their output. And what they did is they used GPT-4, or I don't know if it is GPT-4 exactly or GPT-4o, to produce solutions in Torah format, which is the Microsoft paper, with code execution feedback. So they took the what they already have and created new synthetic dataset that kind of like suits this particular format. You have the rational, you have got the Python program, then you have got the output, all using GPT-4 to create the synthetic dataset on which they can do the fine tuning. This is a very interesting aspect. I've seen a lot of people using synthetic dataset, but mostly for natural language questions. But it is fascinating to see that you can prompt GPT-4 to generate a synthetic dataset that looks like this, and that can also help you with highly successful scores. So fine tuning on this data produces a reasoning agent that can solve mathematical problems via mix of natural language reasoning and also use Python REPL to compute intermediate result. As you can see here, natural language reasoning and a Python REPL to finally get the reasoning, the result out. A rational based one, a Python program based one, but now this is TIR, where you combine both the reasoning and the rational base and the Python program base, which ultimately gives you the final result. And this is the details about their stage 1 and stage 2. Unlike most fine tuning these days, they did not use a LoRa or a Dora. They used a full fine tuning of the weights. So they, in both the stages, we performed full fine tuning where all the weights of the model are updated during back propagation. This is again another interesting choice that they have made. So in other words, we did not use parameter efficient techniques like LoRa or Dora because we were not confident they could match the performance of full fine tuning without significant experimentation. Probably this turned out to be well for them. To accelerate training, we use packing feature from TRL. Okay. And there are other aspects that you could see. So stage 1, this is the learning rate. Stage 2, this is the learning rate. Again, I'm quite used to 1e minus 0.5 or 0.6, but this is another nice interesting learning rate. Total batch size, block size. So this is kind of their the block size that they use. Number of epoch is just 3 and 4. The LR scheduler, the learning rate scheduler, so that it helps with variable learning rate, and then the warm-up ratio. So the initial submissions used a DeepSeek 7 billion parameter models that were only fine-tuned on stage 1, but we found the performance quite limited. Just they got 8 out of 10. So just merely using DeepSeek 7 billion parameter model with the first stage fine-tuning, they could only go 5 above what Gemma did. Gemma did 3 billion parameters. So that is like the 3 out of 50. That is the vanilla model. The vanilla model did 3 out of 550, while the DeepSeek 7 billion with the first stage fine tuning got only 8 out of 50. Thanks to Abdul Rafi's public notebook, they kind of realized that they have to go beyond that. So they used another technique called MMOS, mix of minimal optimal set. I'm not getting into it, but even then they were capped only at 16 out of 50 on public leaderboard. And they've got like majority voting and all the other things, and that is where they started going into further direction, where they started using self-consistency with tool integrated reasoning, because the vanilla solution that they created after the first one, it had a lot of variability and they wanted a more robust solution. So what they do is, for every question, they're going to repeat the question n number of times. Like in this case, let's say 3 number of times. For each problem, copy the input n number of times, in this case 3 number of times, to define the initial batch of prompts to feed to VLLM. These effectively define the number of candidates. So whatever that they split the question into, for example, you have got the question, you split it into 3 times. I mean, not split, duplicate it into 3 times. That is the number of candidates that you are going to get for majority voting. So that is the n number of times. As you can see in the screenshot, it is 3 times. Now, out of the sample, the n number of times, sample n completions until a complete block of Python code is produced. So you sample until at least like there is a complete Python code is produced. Execute each Python block and concatenate the output, including tracebacks and appear. So as you can see here, this is without any Python, this is with Python, and then you have the Python REPL, and this one is without one. So now you can see that there are 3 candidate answers. One is 144, 144, 2002, and using majority voting, you pick the majority answer, and that becomes the correct answer. So according to them, this gave them more robust answer, less variance. So for our winning submission, we generated 48 candidates. So for every question, they generated 48 candidates with a depth of M4. M is like the number of times they generated until they produced a valid Python. So repeat M times. So they are repeating it M times to produce a set of reasoning traces with N depth and M depth. N width and M depth. So as you can see here, they have got input output, which is one simple, then input output with chain of thought, then input output with self consistency with chain of thought, and this is what they, I think, kind of they did, like the tree of thought output. So overall, I'm not even sure if they actually used it, honestly speaking. So ineffective, this algorithm lies somewhere in between self consistency, chain of thought, and tree of thoughts. but doesn't include backtracking or look ahead of to plan the next step of decoding. It's just the normal decoding, just next word. One interesting detail is that they quantized all the models using AutoGPT-Q, and they used 8-bit precision, and even with 8-bit precision they finally managed to get good answer, because they said that they used with majority voting, like in practice, this led to a small drop in accuracy, but was mostly mitigated by being able to generate many candidates during inference. That is another very interesting approach. One is to have a really high precision large language model and get the solution, but the other one is to have the quantized models but generate more candidates and now do majority voting. Overall, it's a very interesting approach. There are a lot of interesting nuggets in it. So they've shared the validation data set that they've shared here. So they talk about the importance of validation data set. They also talk about other ideas that they trained. So just simply training a pure chain of thought model and using majority voting for evaluation, training an MMOS model, which is what they shared here, what they started with, and training that MMOS to solve the problems with Python, just to do it with Python. But somehow they also realized that having a single Python code may not be enough. So this has a lot of interesting detail. I'll strongly encourage you to read it. But if there is one takeaway that you would like to take, this is a very logical approach and with an engineering mindset. So you can see here what we typically do when we get a question, we put it into LLM, get the answer, finish it. That is the Gemma approach, the baseline, the 3 out of 50 approach. But because this is a Kaggle competition and they can just go hard and hard, they went ahead with 2 stages of training approach, where they also try to convert a natural language a math problem into a natural language reasoning, which converted into a code plus tool integration, which finally gave them the output. And also they used solutions like self-consistency and majority voting with more candidates, which further made them solve more problems. More than the model, I'm quite interested in the approach, and that is why I managed to create a video. There are more solutions in the leaderboard. If there is an interest, I would love to discuss more. Strongly encourage you to go read the winner solution, which I'll link it in the YouTube description. If you have got any thoughts, let me know in the comment section. See you in another video. Happy prompting.